February 12th, 1943. The night sky over Hamburg burns with searchlight beams slicing through cloud cover like surgical scalpels. Flight Lieutenant Robert Chen sits in the navigator's seat of a Lancaster bomber, watching his radio altimeter flicker and die. Around him, the rest of the Pathfinder squadron's navigation instruments spin wildly, rendering useless by invisible waves of German jamming signals. The target markers they were supposed to drop with precision now might as well be scattered by coin toss. Below, the city spreads in darkness, protected not by flak or fighters alone, but by something far more insidious: electronic warfare. The Germans called it Störsender. Jamming transmitters. Massive ground stations pumping out radio noise across every frequency the Royal Air Force used for navigation and communication. The result was chaos in the sky. Bombers scattered across hundreds of square miles, unable to coordinate, unable to navigate, unable to find their targets. Chen's pilot, squadron leader James Morrison, banks hard to port as another Lancaster nearly collides with them in the confusion. Without radio contact, without functioning instruments, they are not a coordinated bombing force. They are 40 individual aircraft flying blind through defended airspace, each crew fighting their own isolated battle against an enemy they cannot see or counter. Morrison makes the decision every Pathfinder pilot dreads. He orders the crew to abort the run and return to base with their target indicators still aboard. It is the third mission this week that has ended the same way. German jamming has transformed Bomber Command's carefully planned operations into expensive failures that achieve nothing except wasting fuel, risking crews, and proving that the Luftwaffe's defensive technology has caught up with British offensive capabilities. Back at Royal Air Force Waddington, Chen files his mission report with the same frustrated conclusions that dozens of other navigators are writing. Navigation equipment jammed, radio communications lost, target not located, mission unsuccessful. The pattern has become so predictable that intelligence officers no longer ask for details. They know what happened. The Germans won another round in the invisible war of the electromagnetic spectrum. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But the Germans did not invent this problem. They simply exploited a fundamental weakness in Allied radio technology that every engineer understood, but no one had solved. Early radio navigation systems like G and Oboe worked brilliantly when they worked, allowing bombers to locate targets with unprecedented accuracy. The systems operated on fixed frequencies, sending synchronized pulses from ground stations that aircraft receivers used to calculate their position through triangulation. In clear air, free from interference, navigators could determine their location to within a few hundred yards, even over Germany. The physics were straightforward. Radio waves travel at the speed of light. If you know the exact time a signal was transmitted and can measure when it arrives, you can calculate distance with mathematical precision. 3 synchronized transmitters create a navigation grid that covers thousands of square miles. Aircraft equipped with the proper receivers can navigate in complete darkness, through clouds, through weather that would have made navigation impossible just a few years earlier. German engineers recognized the vulnerability immediately. Fixed frequency systems could be jammed by transmitting noise on the same frequency. The jamming signal did not need to be sophisticated. It just needed to be loud enough to overwhelm the legitimate navigation pulses. A few powerful transmitters scattered across occupied Europe could render the entire British navigation network useless whenever Bomber Command launched major operations. The Luftwaffe established jamming stations at Wangerooge, Ostend, and Cherbourg by late 1942. Each installation housed massive transmitters connected to directional antennas that could focus jamming energy toward incoming bomber streams. German radar operators would detect the British formations and activate the jammers, flooding Allied radio frequencies with noise that made navigation equipment completely unreliable. The jamming was crude but devastatingly effective. It did not matter how precisely British ground stations transmitted their navigation signals if German transmitters could drown those signals in electronic noise. Bomber crews would see their instruments flicker and die as they crossed into range of the jamming stations. Suddenly, carefully planned routes became uncertain guesses. Precision bombing became area bombing, not by choice but by necessity. British scientists at the Telecommunications Research Establishment understood the problem perfectly. They had predicted that the Germans would eventually develop effective jamming capabilities. What they did not have was a solution. Every proposal to defeat the jamming required either abandoning radio navigation entirely, which would cripple Bomber Command's effectiveness, or developing entirely new technologies that did not yet exist. Some suggested increasing transmitter power to overcome jamming through brute force. The mathematics showed this approach was futile. The Germans could always build more powerful jammers closer to the bomber routes. The fundamental advantage belonged to the defender operating ground-based transmitters with unlimited power supplies against aircraft carrying equipment that had to fit in cramped fuselages and operate on limited electrical power. Others proposed using multiple frequencies, forcing the Germans to jam several channels simultaneously. This helped marginally, but did not solve the core problem. German jamming stations could sweep across entire frequency bands, and the limited number of usable radio frequencies meant that spreading the navigation signals across multiple channels only diluted their effectiveness while giving the Germans more targets to attack. The technical specifications seemed to define an impossible requirement. The navigation system needed to operate on frequencies that German jammers could not predict or anticipate. It needed to change frequencies faster than German operators could detect and respond. It needed to maintain synchronization between ground stations and aircraft receivers while constantly shifting across the radio spectrum. And it needed to do all this with 1940s technology vacuum tubes, mechanical switches, and analog circuits. Every experienced radio engineer knew that such a system was theoretically possible, but practically impossible to build. The timing requirements alone seemed beyond the capabilities of existing technology. Switching frequencies meant retuning circuits, which took time. Maintaining synchronization while constantly changing frequencies required clock accuracy that exceeded what was available in field deployable equipment. And the system had to be reliable enough to operate in combat conditions, not just in laboratory demonstrations. The British had invested heavily in their existing navigation systems. G stations covered England and reached into occupied Europe. Oboe provided precision guidance for pathfinder aircraft. H-2S radar allowed bombers to identify targets through clouds. These systems represented millions of pounds in development costs and deployment infrastructure. Abandoning them to start over with entirely new technology seemed impossible, given the time constraints and resource limitations of wartime production. But the alternative was accepting that German jamming would continue degrading Bomber Command's effectiveness until the strategic bombing campaign achieved nothing except high casualties and wasted resources. Air Chief Marshal Arthur Harris watched his carefully planned operations deteriorate into scattered attacks that inflicted minimal damage while losing aircraft to flak and fighters at unsustainable rates. In Washington, a different kind of war was being fought. American military planners were preparing for daylight bombing operations over Europe using formations of heavily armed B-17 and B-24 bombers. The Americans had studied British night bombing operations and recognized that German jamming posed an equally serious threat to their planned campaign. If the Luftwaffe could blind British night bombers, they could certainly do the same to American daylight formations that operated in even more predictable patterns. The United States Army Air Forces had developed their own radio navigation systems based on similar principles to British equipment. Radio range stations provided navigational guidance, communications, networks, coordinated bomber formations. The systems worked well in training exercises over friendly territory. But American engineers knew that once their bombers entered defended airspace over Germany, those systems would face the same jamming that had proven so effective against the Royal Air Force. The technical requirements for defeating jamming were identical on both sides of the Atlantic. Fixed-frequency systems were vulnerable. Multi-frequency systems were marginally better but still inadequate. What both air forces needed was a navigation and communication system that could not be jammed by any practical defensive measure. a system that operated on frequencies that changed so rapidly and unpredictably that enemy jammers could not follow. A frequency-hopping radio that could dance across the electromagnetic spectrum faster than defenders could react. The physics of such a system were understood. Theoretical papers had described frequency hopping as a jamming countermeasure since the 1920s. But theory and practical engineering were separated by technological barriers that seemed insurmountable. Building a radio transmitter that could switch frequencies in milliseconds required components that did not exist. Synchronizing multiple transmitters and receivers to hop in perfect coordination required timing precision beyond what field equipment could achieve. And then there was the human factor. Even if engineers could build frequency-hopping radios, could they manufacture them in sufficient quantities to equip hundreds of bombers? Could maintenance crews in forward airfields keep them operational? Could aircrew learn to use them under combat stress? The gap between laboratory demonstrations and operational deployment had killed many promising technologies that worked perfectly in controlled conditions but failed catastrophically in the chaos of actual warfare. The German jamming campaign intensified. Throughout early 1943, Luftwaffe Signals Intelligence monitored British radio traffic and adjusted jamming strategies to maximize disruption. New jamming stations came online in the Netherlands and Belgium, creating overlapping coverage that made it nearly impossible for bombers to navigate accurately once they crossed the occupied coast. Bomber command casualties increased. Aircraft that could not navigate properly wandered into heavily defended zones or collided with other bombers in the darkness. Missions that should have concentrated hundreds of bombers over a single target instead scattered them across entire regions, diluting the bombing effect and making it easier for German fighters and flak to destroy individual aircraft. The strategic bombing campaign that was supposed to cripple German war production was instead demonstrating the effectiveness of German electronic warfare. British and American scientists knew they were losing a critical technological race. The Germans had achieved local superiority in the electromagnetic spectrum, and unless Allied engineers could develop effective countermeasures, the bombing campaign would continue to fail, regardless of how many aircraft were built or how bravely crews pressed their attacks. The solution existed somewhere in the realm of radio engineering and electronics. Someone just needed to figure out how to make it work with the limited technology available in the middle of a global war. The answer would not come from military laboratories or established defense contractors. It would come from an unexpected source. A radio engineer working on a completely different problem, who stumbled onto a solution that seemed impossible until someone actually built it and proved that impossible was just another word for not yet achieved. But before that breakthrough could happen, more missions would fail, more crews would be lost, and the strategic bombing campaign would continue to demonstrate that in Biblia-Prosent, modern warfare, the invisible battles fought in the electromagnetic spectrum could be just as decisive as the visible battles fought with bombs and bullets. The Battle of Hamburg in July 1943 would expose both the potential and limitations of existing bombing technology. Over 7 nights and 2 days, Bomber Command would launch Operation Gomorrah, attempting to destroy Germany's second-largest city through concentrated incendiary attacks. The operation would demonstrate what massed bomber formations could achieve when conditions favored the attackers. It would also reveal the continuing vulnerability of Allied navigation systems to German countermeasures. The first raid on the night of July 24th dropped over 2,000 tons of bombs, creating a firestorm that killed an estimated 42,000 civilians and destroyed massive areas of the city. But subsequent raids showed decreasing effectiveness as German defenses adapted and jamming intensified. By the final attacks on August 2nd and 3rd, German night fighters, guided by improved radar and coordinated through unjammed radio networks, were inflicting heavy casualties on bomber formations whose own communications remained disrupted. The lesson was clear. Offensive success required not just more bombers or better bombs, but technological superiority in the invisible realm of electronic warfare. The side that could communicate, navigate, and coordinate while denying those capabilities to the enemy would control the night sky regardless of how many guns or fighters they deployed. And in mid-1943, that advantage belonged to Germany. Air Chief Marshal Harris understood the strategic implications. He could send 1,000 bombers over Germany, but if German jamming prevented precise navigation and coordination, those 1,000 aircraft would be far less effective than 100 aircraft equipped with unjammable navigation systems. Quality of equipment now mattered, more than quantity of aircraft. Bomber Command needed a technological breakthrough, not more training or better tactics. American planners reaching similar conclusions as they prepared for their own bombing campaign. The 8th Air Force was building up strength in England, preparing to launch daylight raids that would complement British night operations. But American confidence in precision daylight bombing depended on formation, coordination, and defensive firepower. If German jamming could break up American formations and prevent coordinated defensive fire, their heavily armed bombers would be vulnerable to concentrated fighter attacks. The requirement was becoming desperate. Allied air forces needed unjammable radio systems, and they needed them before German electronic warfare capabilities improved further. Every month of delay meant more failed missions, more lost crews, and more time for German defenses to perfect their jamming techniques. The technological race had become a race against time, and time was running out for the strategic bombing campaign that both Britain and America had placed at the center of their plans for defeating Nazi Germany. The solution would emerge from an unlikely collaboration between military necessity and civilian ingenuity. A radio engineer who understood the physics of frequency hopping would figure out how to make it work with existing technology. The breakthrough would not require inventing new components or waiting for advanced electronics. It would require rethinking how existing equipment could be used in ways that seemed impossible until someone actually did it. But that breakthrough was still months away. In the spring of 1943, Bomber Command crews continued flying missions with navigation equipment that German jammers could neutralize at will. American bomber crews prepared for operations knowing their radio systems were equally vulnerable, and German signals intelligence officers congratulated themselves on winning the electronic warfare battle that was making Allied strategic bombing increasingly ineffective despite growing numbers of aircraft and crews committed to the campaign. The stage was set for a technological revolution that would transform radio communications and navigation for the rest of the war and far beyond. Frequency hopping radio would prove to be one of those rare innovations that works better in practice than in theory, that solves problems engineers thought were unsolvable, and that changes the fundamental assumptions about what is possible in electronic warfare. But before any of that could happen, someone had to build the first working prototype and prove that the impossible was actually just difficult. The breakthrough came from an unexpected source and in an unexpected form, not from a military laboratory or government research facility, but from commercial radio engineering and the desperate improvisation that characterized so much wartime: technological development. The story of how Allied bombers became unjammable is the story of how a few engineers refused to accept that German jamming superiority was permanent, how they found solutions in places no one else was looking, and how they turned theoretical physics into practical equipment that saved countless lives and helped win the air war over Europe. Squadron leader Morrison flew his 43rd mission on March 16, 1943. The target was Stuttgart, an industrial city deep in southern Germany. The navigation systems worked well until the bomber stream crossed into occupied France, where German jammers activated and rendered the equipment useless. Morrison navigated by dead reckoning and celestial observation, techniques that would have been familiar to mariners in the age of sail. His Lancaster dropped its bombs somewhere over southern Germany, possibly near the target, possibly not. There was no way to know. When Morrison returned to base and filed his mission report, he added a personal note to the intelligence officer. "We cannot continue operating this way. German jamming is winning the war they're fighting, and we need our engineers to start winning the war we're fighting. Whatever it takes, we need radio systems that work in spite of German countermeasures, not systems that fail the moment we cross into defended airspace." The intelligence officer filed the report with dozens of others expressing similar frustrations. The complaints were forwarded to Bomber Command headquarters, where they joined a growing pile of evidence that the electronic warfare situation had become critical. Something had to change, and it had to change soon, before the strategic bombing campaign collapsed under the weight of its own technological obsolescence. That change was already in development, though few people knew it yet. A small team of engineers working on what seemed like an unrelated problem had stumbled onto a solution that would transform radio communications. Their breakthrough would prove that frequency-hopping radio was not just theoretically possible, but practically achievable with existing technology. And once they proved it could be done, the transformation of Allied bombing operations would follow with remarkable speed. The electromagnetic spectrum was about to become a battlefield where Allied forces could compete on equal terms with German defenders. The age of unjammable communications was beginning, though the German signals intelligence officers monitoring British radio traffic did not yet realize that their jamming superiority was about to become obsolete. The solution came from a place no military planner would have predicted. The Philco Corporation, a commercial radio manufacturer in Philadelphia, had been working on civilian broadcasting equipment when the war started. Their chief engineer, a man named Leonard Kreyer, had spent the 1930s developing automatic frequency control systems for commercial radio stations. The work had nothing to do with military applications. It was about keeping broadcast signals stable and preventing interference between stations sharing crowded frequency bands. Kreyer understood a fundamental principle that most military radio engineers had overlooked. Frequency changes did not have to be slow. The limiting factor was not the physics of radio waves, which could shift frequencies essentially instantaneously. The limitation was in the mechanical switching equipment that changed transmitter and receiver tuning. Vacuum tube circuits could be designed to retune in milliseconds if you abandoned traditional mechanical switch designs and used electronic switching instead. Electronic switching meant using vacuum tubes themselves as the switching elements. A tube could be turned on or off by changing the voltage on its control grid, and that change could happen in microseconds. String together multiple tubes in a switching matrix, and you could create a radio transmitter that hopped between preset frequencies faster than any human operator or mechanical system could follow. The theoretical maximum switching speed was limited only by how fast the tubes could respond to control voltage changes. Kreyer had built experimental frequency-agile transmitters for testing interference rejection in commercial broadcasting. The systems were never deployed commercially because peacetime broadcasting did not require anti-jamming capabilities. But when Philco converted to war production in 1941, Kreyer mentioned his frequency-switching experiments to a visiting Army Signal Corps officer who was surveying civilian electronics companies for technologies that might have military applications. The Signal Corps officer, Captain Thomas Reardon, immediately recognized the potential. He asked Kreyer if the frequency switching could be made automatic and synchronized between multiple transmitters and receivers. Kreyer said, it could, in principle, though he had never built such a system. The engineering challenges were significant, but not impossible. What was needed was a control system that could tell both transmitter and receiver when to switch frequencies, and ensure they switched to the same frequency at exactly the same time. Reardon arranged funding for Philco to develop a prototype frequency-hopping radio system. The contract was modest, just $50,000, because no one in the Signal Corps really believed the technology would work outside laboratory conditions. But Reardon had seen enough failed radio systems to know that sometimes the most promising solutions came from civilian engineers who did not know what was supposed to be impossible. Kreyer assembled a small team, 5 engineers working in a converted warehouse building in North Philadelphia. Their goal was to build a radio system that could hop between 100 different frequencies in a predetermined pattern, switching frequencies every 50 milliseconds. At that switching speed, the system would complete 20 frequency changes per second, making it essentially impossible for enemy jammers to follow. The synchronization problem was the hardest part. Both transmitter and receiver needed to hop to the same frequency at exactly the same time, or they would be transmitting and receiving on different frequencies, and no communication would occur. Kreyer's solution was elegant. He used a mechanical device similar to a player piano roll, a long strip of paper with holes punched in specific patterns. The paper strip moved through a reader at constant speed, driven by a precision motor. As the paper moved, metal contacts would drop through the holes, completing electrical circuits that controlled which frequency the radio was tuned to. The pattern of holes determined the hopping sequence. As long as transmitter and receiver had identical paper strips and their motors ran at exactly the same speed, they would hop in perfect synchronization. If one machine got out of sync, you could manually adjust the motor speed or physically reposition the paper strip until synchronization was restored. The paper strip system was crude but reliable. It used proven technology that could be manufactured in quantity and maintained by technicians with basic training. Each paper strip was essentially a program that controlled the hopping pattern. You could create different strips for different missions or operational requirements. An operator could load a new strip in seconds, changing the entire hopping sequence instantly. The first prototype was ready for testing in August 1942. Kreier's team set up a transmitter in their Philadelphia warehouse and a receiver at a signal corps facility 30 miles away. They activated both systems simultaneously, synchronized their paper strip drives by radio coordination, and began testing. The initial results were disappointing. Synchronization was difficult to maintain. The paper strips stretched and tore. The mechanical readers jammed. The vacuum tube switching circuits overheated. But Kreier was methodical. He redesigned the paper strip transport to reduce mechanical stress. He improved the vacuum tube cooling. He developed better synchronization procedures. By November 1942, the system was working reliably over short distances. The Signal Corps authorized continued development and increased funding to $200,000 for building field-deployable prototypes. The British learned about Kreier's work through the usual channels of Anglo-American technical cooperation. A telecommunications research establishment scientist named Robert Hanbury Brown visited Philadelphia in December 1942 to evaluate the frequency hopping system for potential Royal Air Force applications. Brown was skeptical. He had reviewed numerous proposed anti-jamming technologies, and most had failed to work in field conditions despite impressive laboratory demonstrations. But when Kreier demonstrated the working prototype, Brown's skepticism evaporated. The system actually worked. It hopped between frequencies fast enough that jamming was essentially impossible. A jammer would need to transmit on all 100 frequencies simultaneously to be effective, which would require 100 times as much power as jamming a single fixed frequency. And even then, the jammer would only interfere with 1% of the transmission time if the frequency hopping system was using 100 different frequencies. Brown wrote an enthusiastic report to the Telecommunications Research Establishment recommending immediate British participation in further development. He noted that the system's genius was not in using advanced technology, but in using existing technology in clever ways. Everything in Kreier's frequency hopping radio could be built with standard radio components available from any electronics supplier. The innovation was in the architecture and control system, not in the individual components. The British contribution came in the form of improved synchronization techniques. Telecommunications Research Establishment engineers had extensive experience with precision timing systems from their radar work. They suggested using crystal-controlled oscillators to drive the paper strip motors, ensuring that transmitter and receiver strip drives ran at exactly the same speed. This eliminated the drift problems that Kreier's team had been fighting with simple AC motors. They also developed better paper strip materials. The original strips were ordinary paper that stretched when humid and became brittle when dry. British engineers substituted a paper polyester laminate that was dimensionally stable across wide temperature and humidity ranges. The improved strips lasted 10 times longer and maintained their timing accuracy even after thousands of cycles. By March 1943, Philco had produced 20 prototype frequency hopping transceivers, designated SCR 584. The Signal Corps conducted field trials at Fort Monmouth, New Jersey, testing the systems under realistic conditions with simulated jamming. The results exceeded expectations. Even when deliberately jammed with transmitters 10 times more powerful than the frequency hopping radios, communications remained clear and reliable. The jamming was simply unable to follow the frequency hops fast enough to be effective. The implications were immediately obvious to anyone who understood electronic warfare. Frequency hopping radios could restore reliable communications and navigation to Allied bombers operating in jammed environments. But there was a problem. The SCR-584 prototypes were large, heavy, and consumed significant electrical power. Each unit weighed 90 pounds and required its own motor generator for power supply. Installing them in bombers would mean removing other equipment or reducing bomb loads. Bomber Command evaluated the weight and power requirements and concluded that the SCR-584 was impractical for installation in existing bombers. The Lancaster could theoretically carry the additional weight, but the electrical load would overstrain the aircraft's generators. The American B-17 had similar limitations. The frequency hopping technology worked brilliantly, but the packaging was wrong for bomber applications. Crayer went back to his engineering team with a new requirement. Design a frequency hopping system that weighed no more than 30 pounds and operated on standard aircraft electrical power. The team protested that this was impossible. The motor generator alone weighed 40 pounds. The paper strip drive mechanism weighed 15 pounds. The vacuum tubes and switching circuits added another 35 pounds. There was no way to cut the weight by 2/3 without eliminating essential components, but impossible was just a starting point for wartime engineers. Crayer's team began a systematic weight reduction program. They replaced the heavy motor generator with a smaller dynamotor that weighed 8 pounds. They miniaturized the paper strip mechanism by using narrower strips and a more compact drive system. They redesigned the vacuum tube circuits to use smaller tubes that generated less heat and required simpler cooling, and they packaged everything in an aluminum case instead of the steel chassis used in the prototypes. The redesigned system, designated SCR-584A, weighed 28 pounds and operated on standard 28-volt aircraft power. It hopped between 50 frequencies instead of 100, reducing the anti-jamming performance slightly, but making the system much simpler and more reliable. The frequency hopping rate increased to 100 times per second, compensating for the reduced number of frequencies by spending less time on each frequency. By June 1943, the SCR-584A was ready for operational testing. The Signal Corps delivered 6 units to the 8th Air Force in England for evaluation in actual combat conditions. The systems were installed in B-17 bombers of the 91st Bomb Group, replacing one of the waist gunner positions to accommodate the equipment and its operator. The first combat test occurred on June 22, 1943, during a raid on a synthetic rubber factory in Hulls. The B-17 formation crossed into German airspace and immediately encountered heavy jamming that disrupted normal radio communications and navigation equipment. But the bombers, equipped with SCR-584A, maintained perfect communications with each other and with ground stations. The navigators reported that their frequency hopping position updates were completely unaffected by German jamming. The mission commander, Major John Harkins, filed a report that Crayer would later frame and hang in his office. The frequency hopping radios performed flawlessly under conditions that rendered our standard equipment useless. German jamming had no noticeable effect on the unjammable communications. This technology needs to be deployed to the entire bomber force immediately. But immediate deployment was not possible. Manufacturing frequency hopping radios required precision components and skilled assembly labor. Philco could produce perhaps 50 units per month with their existing facilities. Equipping the entire 8th Air Force would take years at that production rate, and Bomber Command needed the equipment just as urgently. What was needed was a crash production program that could manufacture thousands of frequency-hopping radios in months, not years. The War Production Board authorized expansion of Philco's manufacturing facilities and licensed the SCR-584, a design to 3 other electronics manufacturers, RCA, Zenith, and Hallicrafters all began tooling up for frequency-hopping radio production in July 1943. The goal was to produce 500 units per month by October and ramp up to 2,000 units per month by early 1944. The British decided to develop their own version of the frequency hopping system rather than wait for American production to meet both countries' requirements. Telecommunications research establishment engineers created a simplified design that used many components already in production for other British radio equipment. The British system, designated TR-5045, hopped between 30 frequencies at 200 times per second. It was less sophisticated than the American design, but easier to manufacture with Britain's more limited industrial capacity. Production began at Standard Telephones and Cables in August 1943. By November, British factories were producing 300 TR-5045 units per month, enough to equip Pathfinder squadrons first, and then gradually expand to main force bomber units. The British installation was even more compact than the American version, fitting into existing radio equipment racks with minimal modifications to the aircraft. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German signals intelligence detected the frequency hopping transmissions in July 1943, but did not immediately understand what they were observing. Monitoring stations reported brief signal bursts that appeared on multiple frequencies in rapid succession, staying on each frequency for only a few milliseconds before jumping to another frequency. The pattern seemed random but repeated with precise timing that suggested automatic control rather than human operation. Luftwaffe radio intelligence officers initially classified the signals as some kind of experimental navigation system. They attempted to jam the transmissions using conventional techniques, flooding individual frequencies with noise. The jamming had no effect. The Allied transmissions continued uninterrupted, hopping around the jammer frequencies faster than German operators could follow. By August, German engineers realized they were facing a new technology that defeated their jamming capabilities. They began developing countermeasures, but the physics of frequency hopping made effective jamming nearly impossible. To jam a frequency hopping system, you needed to transmit on all possible frequencies simultaneously, which required enormous power and would interfere with your own communications. Or you needed to predict which frequency the system would hop to next and jam that frequency before the transmission arrived. The prediction approach required knowing the hopping pattern. German signals intelligence threw substantial resources at trying to determine the hopping sequences. They recorded hours of Allied frequency hopping transmissions and analyzed the patterns using the best cryptanalytic techniques available. But the hopping patterns were generated from paper strips that could be changed daily or even for each mission. Breaking one pattern provided no information about future patterns. The Allies had created a virtually unbreakable communications system using nothing more sophisticated than punched paper and vacuum tubes. German countermeasure development focused on barrage jamming, transmitting across entire frequency bands rather than individual frequencies. This approach worked to some degree, but it required so much power that only a few ground stations could implement it, and it interfered with German communications just as much as Allied transmissions. The Luftwaffe found itself in the position of having to choose between allowing Allied frequency hopping communications to operate freely or jamming so broadly that their own radio networks became unusable. The strategic impact became apparent by late 1943. Allied bomber formations, equipped with frequency-hopping radios, maintained communications and navigation capability throughout their missions, regardless of German jamming. Pathfinder aircraft could coordinate target marking with precision. Bomber streams could execute planned routing and timing. Formation leaders could issue tactical commands that reached their entire force. The coordination that German jamming had disrupted for nearly a year was suddenly restored. The difference in bombing accuracy was measurable. Missions using frequency-hopping equipped Pathfinders put twice as many bombs within 1 mile of the target compared to missions relying on jammed conventional navigation. The improved accuracy meant that fewer bombers were needed to achieve the same level of destruction, reducing aircraft losses and crew casualties. The frequency-hopping technology was not just defeating German jamming, it was making the entire strategic bombing campaign more efficient and effective. American daylight bombing operations benefited even more dramatically. B-17 and B-24 formations depended on tight defensive tactics that required reliable radio communications between aircraft. German jamming had threatened to break up these formations, making individual bombers vulnerable to fighter attacks. Frequency-hopping radios restored formation cohesion and allowed the defensive tactics that made American daylight bombing feasible, despite heavy fighter opposition. By January 1944, over 800 Allied bombers were equipped with frequency-hopping radios. The number continued increasing as production ramped up and installation teams worked through the bomber inventory. By D-Day, in June 1944, virtually every Pathfinder aircraft and one bomber in 3 carried frequency-hopping equipment. The electromagnetic spectrum that had been dominated by German jamming was now contested territory where Allied technology provided equal or superior capability. The German response evolved slowly, constrained by industrial capacity and technical limitations. They deployed more powerful jamming transmitters and attempted to develop their own frequency-hopping systems. But Allied bombing of German electronics factories disrupted production of sophisticated radio equipment. The Germans were trying to match Allied innovation, while simultaneously defending their industrial base from the bombing campaign that frequency-hopping radios had made more effective. Luftwaffe night fighters adapted to the new electronic environment by relying more heavily on radar and visual observation rather than radio coordination. This worked to some degree, but it reduced the efficiency of German defences and forced fighters to operate more independently rather than in coordinated groups. The loss of reliable radio communications degraded German defensive capabilities in subtle ways that compounded over thousands of sorties. The effectiveness of frequency-hopping radios extended beyond jamming resistance. The systems provided inherent security against eavesdropping. German listening posts could detect that transmissions were occurring, but they could not reconstruct the message content because they were only receiving brief fragments on individual frequencies. The complete message existed only when all the frequency fragments were reassembled by a synchronized receiver using the same hopping pattern. Intercepted signals were useless without knowing the hopping sequence. This communications security feature proved valuable for operational security. Allied planners could discuss mission details over frequency-hopping radio networks without fear that German intelligence would intercept useful information. The traditional security precaution of radio silence before major operations became less critical when communications were both unjammable and unreadable by the enemy. This operational flexibility improved coordination and reduced the fog of war that had previously complicated bomber operations. The technology spread beyond bomber operations. Fighter escorts received frequency-hopping radios that allowed reliable coordination between escort fighters and the bomber formations they protected. Ground control stations used frequency hopping to provide weather updates, routing changes, and tactical intelligence to formations already over enemy territory. The entire air operations system became more responsive and adaptive because reliable communications persisted throughout missions regardless of enemy countermeasures. Technical improvements continued throughout 1944. The SCR-584B increased the number of hopping frequencies to 75 and reduced weight to 23 pounds. The British TR-5045 Mark II improved reliability and extended battery life for emergency operation if aircraft power failed. Both systems incorporated lessons learned from operational use, addressing problems that had not been apparent during testing but became obvious during combat operations. Maintenance procedures evolved to support field repairs and paper strip replacement. Ground crews learned to synchronize the systems quickly before missions and troubleshoot common problems without requiring specialized test equipment. The frequency-hopping radios proved more reliable than conventional radio equipment, partly because the redundancy of hopping across multiple frequencies meant that even if some frequencies were unusable due to equipment problems, enough frequencies remained operational to maintain communications. The paper strip control system, initially seen as a crude expedient, proved remarkably robust. The strips were inexpensive to produce and easy to distribute. Security officers could generate new hopping patterns by creating new paper strips, then distribute the strips. to all aircraft scheduled for a particular mission. If strips were captured or compromised, new patterns could be implemented immediately, without requiring any changes to the radio equipment itself. The separation of the control pattern from the hardware provided operational flexibility that more sophisticated electronic control systems could not match. The strategic bombing offensive reached its peak effectiveness in 1944, and frequency-hopping radio technology was a significant contributor to that success. Squadron leader Morrison, who had aborted that mission over Hamburg in February 1943 due to jamming, flew his 72nd mission in April 1944. His Lancaster was equipped with a TR-5045 frequency-hopping radio. The German jamming stations were still operating, but Morrison's aircraft hopped around the jamming effortlessly, and the bombs fell within 300 yards of the target. The statistical record tells the Park story with cold precision. In the first half of 1943, before frequency-hopping radios were deployed, Bomber Command's average bombing error was approximately 2 miles. In the second half of 1944, with frequency-hopping navigation widespread, the average bombing error dropped to less than half a mile. The same number of bombs delivered twice the destruction to intended targets because the navigation systems actually worked. The frequency-hopping systems proved their value most dramatically during the D-Day invasion. On the night of June 5th and 6th, 1944, over 1,000 Allied bombers attacked coastal defences in Normandy. German jamming was at maximum intensity. Every available transmitter along the French coast was activated to disrupt Allied communications and navigation. But the Allied aircraft, nearly all equipped with frequency-hopping radios by that date, maintained their schedules and hit their targets with devastating accuracy. General Dwight Eisenhower noted in his report that the frequency-hopping radio systems had performed flawlessly under the most challenging operational conditions of the war. The German perspective on frequency-hopping technology was one of frustration and grudging respect. Colonel Werner Hoffmann commanded the Luftwaffe Signals Intelligence Service in France during 1944. In July 1944, he wrote, "The enemy has achieved communications superiority through frequency-agile radio systems that our jamming cannot affect. The electromagnetic spectrum, which we dominated a year ago, is now firmly in enemy control." Allied bombing operations in the summer and fall of 1944 achieved accuracy and coordination that would have been impossible without frequency-hopping communications. The systematic destruction of German oil production, transportation networks, and industrial facilities proceeded according to plans that depended on reliable navigation and communications. German defences could not effectively counter the Allied bombing campaign. The final months of the European war saw Allied air superiority become so complete that German defences could barely interfere with bombing operations. The Luftwaffe fighter force was crippled by fuel shortages and attrition. German jamming continued, but frequency-hopping radios made the jamming irrelevant. Allied bombers roamed across Germany in daylight, hitting targets with precision that would have seemed impossible in 1943. Leonard Kreyer received the Medal of Merit from President Truman in October 1945. The citation noted that his development of frequency-hopping radio systems had contributed materially to the success of Allied air operations and the ultimate defeat of enemy forces. In his acceptance speech, Kreyer made a point that would prove prophetic. The frequency-hopping technology we developed for military communications has applications far beyond warfare. I believe this technology will transform commercial communications in the decades ahead. He was correct. Frequency hopping remained classified military technology throughout the 1950s and 60s. The declassification in the 1970s opened the door to commercial applications. Engineers discovered that frequency hopping was ideal for cordless telephones, wireless data networks, and mobile communications systems. The same principles that had defeated German jamming in World War II could defeat interference in crowded radio frequency environments. The most widespread application came with the development of Bluetooth wireless technology. Bluetooth uses frequency hopping across 79 different frequencies, switching frequencies 1,600 times per second. Every Bluetooth device, from wireless headphones to computer keyboards, uses the frequency hopping technique that Leonard Kreyer pioneered in 1942. Cellular telephone systems incorporate frequency hopping as a standard feature. Your mobile phone conversation hops between frequencies hundreds of times per second. The global cellular network that connects billions of people uses technology descended directly from the SCR-584, a radio installed in B-17 bombers, in 1943. Modern military radios use frequency hopping combined with encryption and spread spectrum techniques to create communication systems that are virtually impossible to jam or intercept. The electronic warfare capabilities that seemed so advanced in World War II are now standard features in every military radio system deployed anywhere in the world. The frequency hopping story illustrated how innovation often comes from unexpected sources. Kreyer was not working on military problems when he developed the concepts that led to unjammable radios. He was solving commercial broadcasting interference issues. The application to military communications was obvious only in retrospect. The engineering methodology that Kreyer employed became a model for wartime technology development. He worked with existing technology and found ways to use it in new combinations that solved problems other engineers thought were unsolvable. Squadron leader Morrison survived the war and returned to civilian life in 1946. He often spoke about the technological transformation he witnessed. "When I started operations in 1942, we were flying missions with equipment that barely worked. By 1945, we had radio systems that the enemy could not jam, navigation equipment that actually worked, and the confidence that comes from technological superiority." Frequency hopping radios were a big part of that transformation. The human cost of the bomber offensive was enormous on both sides. Over 110,000 Allied aircrew were killed in operations over Europe. German civilian casualties from bombing exceeded 500,000. The technology that made bombing more accurate did not make it less deadly, but it did make it more strategically effective. Targets that needed to be destroyed were destroyed with fewer wasted bombs and fewer misaimed attacks on non-military areas. The historical significance of frequency hopping radio extends beyond its immediate wartime impact. It represented a fundamental shift in how engineers approached reliable communications in contested environments. Instead of trying to prevent jamming through power or signal strength, frequency hopping avoided jamming by never staying on a jammable frequency long enough to be affected. The conceptual breakthrough was as important as the technical implementation. The civilian benefits of this military technology are difficult to overstate. Wireless communications that now seem ordinary and ubiquitous exist because engineers in the 1940s figured out how to make radios hop between frequencies fast, enough to avoid jamming. Your smartphone, your wireless internet, your Bluetooth devices, your GPS navigation all incorporate frequency hopping or related technologies descended from wartime anti-jamming research. The bomber crews who flew missions over Germany in 1944 had no idea that the bulky radio equipment in their aircraft would eventually lead to wireless communications devices carried by billions of people. They just knew that their radios worked when nothing else did, that they could navigate accurately despite German jamming, and that the technology gave them a fighting chance to complete their missions and return home. Leonard Kreyer died in 1987 at the age of 82. His obituary mentioned his World War II work briefly, but most people reading it had no idea how profoundly his engineering had influenced modern communications. The frequency hopping principle he developed was by then so thoroughly integrated into wireless technology that it had become invisible infrastructure, unnoticed precisely because it worked so well. The strategic bombing campaign ended with the German surrender in May 1945. The frequency hopping radios that had helped make the campaign effective were largely forgotten in the post-war accounting of how victory was achieved. The invisible electronic warfare that made accurate bombing possible received less attention, even though it was just as essential to the campaign's success as the bombers themselves. The electromagnetic spectrum that had been a battlefield in World War II remained contested territory throughout the Cold War and into the 21st century. The frequency hopping techniques pioneered in 1942 evolved into increasingly sophisticated electronic warfare systems. But the fundamental principle endured. When communications are essential and jamming is inevitable, the solution is not to fight the jamming directly. The solution is to move so fast that the jamming cannot follow. That principle, refined and proven in the skies over Germany during World War II, continues protecting military communications and enabling civilian wireless technology today. Every time you make a phone call, connect to wireless internet, or use a Bluetooth device, you are benefiting from the engineering work that Leonard Kreyer and his team performed in a Philadelphia warehouse in 1942. The frequency-hopping radio that made Allied bombers unjammable also made the wireless world possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.